Good afternoon, ladies and gentlemen. Welcome to the ninth lecture of the Taiwan Bridge program at Academia Sinica. We are honored to welcome Professor Wüthrich, recipient of the 2002 Nobel Prize in Chemistry, to deliver a distinguished keynote lecture. My name is Bruce Yu, Research Fellow and Deputy Director at the Institute of Chemistry, Academia Sinica. First, I would like to thank the International Peace Foundation together with Academia Sinica for organizing and supporting of this wonderful event. So before the lecture, I would like to invite President of Academia Sinica, Dr. James Liao, to give us an opening remark. Please join me for a welcome to President Liao.
Good afternoon, ladies and gentlemen. It is my great honor to welcome you to this afternoon's special lecture organized by Academia Sinica, International Peace Foundation, as well as the National Taiwan University, along with many other universities in Taiwan. This year, we invited more than 30 Nobel laureates to visit Taiwan to give us a series of lectures. And today is our great pleasure to have Nobel Laureate Kurt Wüthrich. He used to be at Scripps and world expert in NMR solution structural biology. And he will tell us his vision about how to do research. But most interestingly, some of you may know that Dr. Wüthrich used to be a professional or close to be professional athlete. And I'm sure that he would show that he exhibits the same kind of rigor in both sports and in science, probably more so in science, and that resulted in his success in his career. I hope you all enjoy this afternoon's seminar. Thank you very much.
So good afternoon, ladies and gentlemen. It is a rare distinct to introduce a speaker whose work has not only redefined the field, but fundamentally redefined. Today, we are joined by Professor Kurt Wüthrich, a scientist whose name is synonymously with the marriage of physics and biology. So let me briefly introduce him. Professor Wüthrich's journey has been in Switzerland, where he studied chemistry, physics, and mathematics at the University of Bern, before obtaining his PhD from the University of Basel. After a period stay in the United States at Berkeley and the Bell Lab, he returned to Switzerland to join ETH Zurich. It was there over the course of several decades, he laid a revolution in structural biology. I want to express revolution is an understatement. So today he continued his prolific work in Scripps, in Zurich, in ETH Zurich, as well as in Shanghai, China. So to understand his contribution, one must look at the state of biology in the late 20th century, while X-ray crystallography allows us to see the skeleton of proteins in crystal form. But these models were static. So Professor Wüthrich's genius lay in his application of NMR, nuclear magnetic resonance spectroscopy, to biological macromolecules. He developed a series of methods and then allowed the scientists to determine the three-dimensional structure of proteins and nucleic acid where they were in solution. So that means we no longer need look at it in the static mode, and we can see them swimming in the solution. We can see them move, bend, and interact with the drugs and the other molecules. So for his transformative work, he was awarded a Nobel Prize in Chemistry in 2002. So the Nobel Committee recognized his work, that his method turned NMR into an unbelievable tool for chemists and biologicals alike, provide us with a deeper understanding of the very building blocks of life, from the way prions causes disease to the way the immune system recognizes invaders. So as President Liao has mentioned, Professor Wüthrich has been a tireless mentor and Also, he's an athlete. I look at several of his videos on the YouTube. He talk about his love of skiing. And also, he brings a legendary discipline and energy to his scientific increase that truly is inspiration to the next generation of researchers. Okay, so let me change gear a little bit. I want to share with you today's topic is AI. So the one I just mentioned to you was created by Gemini. I am actually trying to share with you some personal thoughts. I am a synthetic and material chemist. I mean, you know, the research I'm conducted was originated from the Nobel Prize in Chemistry in year 2000 and 2001. So even my work has been a little bit further away from Professor Wüthrich's work. His research is highly recognized even by scientists like me. And I want to share with you one single image in here, because when I was coming back to Sinica, I was working in Riken in Japan from 2008 to 2014. And this was part of the Riken Yokohama campus. You can see there all these Mongolian yurt-like buildings were part of the creation of Professor Wüthrich's work, because he brings the impact to the society which you were able to convince the politicians to invest on science, create all those beautiful structures. If you know them, each of them has a single NMR in it, high frequency NMR. I know scientists sometimes people don't understand it, but with Professor Wüthrich's work, he brings real impact to the society and to the community. So today we are here to learn from a master of molecule architecture. So with that, please join me in a warm and appreciated welcome for pioneer, a Nobel Laureate, and the visionary scientist, Professor Kurt Wüthrich.
Good afternoon, everybody. Thank you so much for the invitation to speak to you here and for the kind introduction. I first presented a lecture at the Academia Sinica 41 years ago. My wife and I visited Taipei and actually most of Taiwan in 1983 on a political mission that is probably closer to the World Peace Foundation than anything else that I'm going to talk about today, because the mission at the time was to make arrangements for the colleagues in Taiwan and the colleagues in mainland China to participate in international science policy in the scientific unions and in ICSU, the International Council of Scientific Unions. As some of you may know, this all happened between 1981 and about 1985, that this was arranged, and it has worked up to today. My title says the molecules of life. And I'll come to this in a minute, what I mean with this. AI stands for artificial intelligence, a word that I don't particularly like, by the way. I would rather refer to it as most efficient bean counting and human health. Now, I will mostly be talking about science today, but before that, I want to spend a few minutes talking about the second important, maybe the most important part of the work that academics who teach the next generations of students need to do. We have to think very carefully these days as to how we should teach our students. What will they need in their professional life? And I'll spend the first few minutes discussing this issue. But before I go to the second slide, just think about the possibility. I mean, I'm taking this from recent Nature editorials which say how universities came to be and why they are in trouble now, or reinventing universities for today's world. One of the ideas here is to use AI to educate our medical doctors. One of the articles in this commentary suggests that by using AI to educate our medical doctors in the early stages of their studies with AI models, rather than having some gain initial experience with real patients, could speed up the education of medical doctors by 30 or 40%, so that they would finish their studies after 8 years rather than 12 years, or possibly 6 years rather than 12 years. I wonder whether this is a good idea, or whether it is not really very useful that we leave those who will care for our health later on in their lives to also mature as human beings while doing their studies and learning the techniques, which will change anyway after they have finished their studies. And I go now on and talk about the Nobel Prize in connection with this idea of how we should educate students in the future. Why do I show Nobel Prize? I wouldn't be here if I didn't have a Nobel Prize. That has already been mentioned. But there is something special about the prize in 2002. We were 3 laureates, John Fen and Koichi Tanaka, who got the prize, one half of the prize for mass spectrometry of proteins, and I got the other half for NMR with proteins. Now look, John Fen did the work that got him the Nobel Prize at age 73, after a career mostly in industry and in institutions of the US government. I mean, not in universities. Only after retirement from these jobs, he went back to Yale, and after 8 years at Yale, he did the work that got him the Nobel Prize, making use of his experience, mostly with jet propulsion problems associated with building rockets in government labs. Then you have Koichi Tanaka. He did his work when he was 23. He didn't have a PhD. He just had a bachelor's degree from a technical school in Japan, went straight to industry, and after a few months discovered a technique that is equivalent to the one by John Fen to enable mass spectrometry of proteins. Then he got the prize at age 43, and I'm sort of in between. I was 46 when I completed the research that was awarded with the prize, and I got it at age 64. Now, especially the more junior people in the audience should take encouragement from this. On the one hand, maybe you are all too old already to equal Tanaka, but most of you have a lot of time to reach the age at which John Wen made his discovery that got the Nobel Prize. And I think that also in the future we will need leaders. We will need some people who are special and make something special. And that can happen at any time. That can happen on the basis of very different lines of education. I think the important thing is that when we have the new generations of students in front of us in the universities, we have to educate them to become personalities, to be able to organize their own lives as a basis for doing ingenious research, and for some of them to make a breakthrough at some point that may lead to future Nobel Prizes. See, here you see the three of us, and here I have put in a few words what I really meant to say in the first few minutes of my talk. The 21st century demands on professional abilities evolve so fast that humans live in states of either permanent adaptation or continued falling behind. You have no third choice. And you can choose whichever you want to do. And it is clear we have to provide our students with a foundation that will enable them to permanently adapt to the next 40 or 45 years of their professional careers after they leave university, either with a BS, an MS, or a PhD degree. And then they may end up even in Stockholm. By the way, when I teach in mainland China regularly. I will teach in Shanghai during the next weeks. And the way to attract the students to come to the lectures is that the title is How to Get a Nobel Prize. Then the students flow in, and my room is full. If I talk about NMR, then they will sleep immediately. All right, now let me get to the theme of my lecture, to the science. Molecules of life, DNA, RNA, and proteins. There are many more molecules, small molecules and larger molecules that sustain our life, but these are what we often refer to as the molecules of life. And the central dogma of molecular biology that you all know, we have replication, DNA to DNA, we have transcription, DNA to RNA, and translation, RNA to protein. And then there are a few thinner arrows linking DNA with protein, DNA with RNA, RNA with protein, and so on. What I'm now going to discuss for proteins applies similarly to RNA and DNA as well. When we look at the chemical structure of these molecules, all three classes, we have a repetition of simple building blocks. 4 building blocks in the case of DNA or RNA, 20 building blocks in the case of proteins. A linear chain containing 20 different building blocks. And these building blocks are chemically different, but not very different. And we could, under no circumstances, understand how so many different functions of proteins could be rationalized by varying the sequence of these building blocks. Just as an illustration, proteins protect us. Our hair is protein, our skin is protein. They catalyze with enzymes. For example, they digest food in our stomach with enzymes. Then we need hormones to regulate processes in our metabolism. We need transport, hemoglobin that transports oxygen from the lungs into the body and enables us to function. And we could not understand, based on knowing the chemical structure of proteins only, how this class of proteins can perform all these widely different functions that I mention here: protection, catalysis, regulation, transport, and many others. We need to know the three-dimensional structure, and only then can we rationalize that proteins can perform such a wide spectrum of functions that support our life and our well-being. How do we determine three-dimensional structures of proteins or nucleic acids? Since the late 1950s, we had X-ray crystallography. Since 1984, NMR with proteins in solution. Since about 2012, and efficiently actually much later, about 2017, cryo-electron microscopy has joined the two other techniques for experimental determination of proteins and multimolecular complexes of proteins, nucleic acids, lipids, and so on and so forth. And most recently, artificial intelligence has been used to predict protein structures using data that have been accumulated with these three techniques. They have trained their algorithms and successfully predicted millions of protein structures. A complete revolution which has immediately been recognized by a Nobel Prize 2 years ago, as you all know. My technique is NMR with protein solutions, and from now on I will talk about NMR with proteins for the remainder of my talk. So what we have achieved is to get three-dimensional protein structures at atomic resolution. That says we can place the individual atoms in three-dimensional space by NMR in solution. And NMR, for those who have not yet learned it, stands for nuclear magnetic resonance. Others say no more research would also fit, no meaningful results would fit, but it is nuclear magnetic resonance. You recognize this molecule, I'm sure. It is water. The two white balls are hydrogen atoms, the red ball is an oxygen atom. and we see a single line when we run an NMR spectrum of water. By the way, I have spent years of my career looking at this line. I'm not kidding you. I have a whole line of publications that are based on looking at this line. That's interesting in itself. But when you then go to more complicated molecules than water, and I'm showing to you here the structure of a small protein. The name is cytochrome C, and this is the presentation of this molecule as it was seen by X-ray crystallography in 1968. There were no computers to draw molecules. There was only this presentation, laminated wood platelets pasted on top of each other so that you can follow some parts of the polypeptide chain. And the black part in the middle is the so-called heme group. That's where the action is, in this case, electron exchange between +3 and +2 oxidation states of the iron. At that time, in the 1960s, artists were hired to turn the results of X-ray crystallography into nice pictures. So this is the same molecule as we have seen here. The painting is by an artist with the name of Erwin Geis, who has painted essentially all the protein structures that were determined up to 1985, because until then there were no computers who were able to make nice drawings of the results from structure determinations. Now, in this particular case, the crystallography, I also ran NMR spectra in 1968. And what you now see is not a single line, as we had it from water, but now we have in this more complex structure a few hundred hydrogen atoms with different chemical structures, which leads to different positions, so that you now don't have a single line, but you have a spread of lines over a large frequency scale, which we in NMR tend to define not by frequency unit, but by parts per million relative to a reference compound. You can see that on the extreme right and on the extreme left, we have nicely resolved lines. From these, we learned about spin physics in a protein in solution. I'll come back to that in a few minutes. That was extremely important. We could do everything with these lines that organic chemists could do with very simple small molecules. And we could do all the experiments that we needed to learn how we can handle nuclear spins in a protein in solution. But you then also see in the middle overlapping resonances of hundreds of lines with different chemical properties. And this was not possible to unravel in one-dimensional NMR spectra like this one. So we faced a number of problems when it was a matter of structure determination in solution. You see, the other two techniques that I mentioned, X-ray crystallography and cryo-EM, they keep their samples fixed. And in order to really keep them fixed, they are also refrigerated to liquid nitrogen temperature, almost minus 200 degrees centigrade. So everything is stiff, and in principle, these methods can work by taking pictures. They like photographic pictures from different sides, and that gives you the picture of the molecule. When you have a running horse, you already get some problems getting a sharp picture usually. And proteins in solution move much faster than a horse can run, and the problem is much more difficult to handle. In addition, it is so that you cannot do NMR in solution unless these spins are in rapid motion. I'll come back to that in a second. But first, we had to resolve the problem of seeing all the lines between, say, 2 and 6 that are strongly overlapped. We had to resolve those. And that was done by introducing multidimensional NMR. First, two-dimensional NMR, and this work was done in collaboration with Richard Ernst, who got the Chemistry Nobel Prize in 1991 for his contributions to the development of NMR. And instead of having a one-dimensional spectrum, we now have a two-dimensional spectrum, and you can see that in this two-dimensional frequency space, the mess in the middle of the spectrum from about 2 to 6 ppm is resolved by having peaks nicely distributed in the two-dimensional frequency plane. Today, it is routine in my laboratory and the laboratories of hundreds of colleagues to run three-dimensional and four-dimensional NMR experiments. We have also done six-dimensional and seven-dimensional NMR experiments. It's all the same principle. The key was to get from 1 to 2 dimensions, and then we could go up from there at will. All right, problem solved. We have a technique that enables us to see all the individual atoms in the protein by resolved lines. Now comes the next problem to be solved. Proteins in solution are under the regime of Brownian motion. Without Brownian motion, we would never see an NMR spectrum, full stop. Okay? And Brownian motion got its name because a botanist, a person who studies plants, Robert Brown, observed in 1827, remember that's 200 years ago, you have to go back in history sometimes when you want to understand things. Robert Brown dropped some pollen from flowers into a water beaker. And then he looked at these pollen in the microscope and discovered that they wouldn't just sit on the water surface, but the pollen would move around. Small pieces of pollen would change direction more frequently than larger pieces of pollen. And this was published in 1827, and Brown didn't understand why it was so. He just found it interesting. He didn't think about NMR or anything similar. He just saw, he was curious. He wanted to know what these pollen did when they fell into the water and described it. It took almost 100 years until this person, of whom you have probably heard in your life before, Albert Einstein, analyzed the observation by Robert Brown. By the way, Albert Einstein did this work about 20 kilometers away from the house where I was born. And he was an employee in the patent office in Bern, in Switzerland, and he wasn't hired to do science. He was hired to work on patent applications and all this administrative stuff. And he analyzed the observation of Brown and further realized a year later, and that was in 1905, in 1906 he realized that Brownian motion was not only lateral motion, but it was also rotational motion. So, I think I have another. So we don't just have sideways movement, but each of these little balls also rotates. And he realized that these rotational and translational motions are due to collisions with thermally agitated solvents, the water molecules. And so that was also the start of statistical mechanics. On the way, very important papers. Einstein lectured exclusively about the Brownian motion between 1905 and 1910, and not about relativity theory or similar. That was also at the heart of his interests, obviously. I haven't talked to him about this, but the literature is very clear about it. And as a result of this, we know that unless there is rapid rotational and translational motion of proteins in solution, then we will not see an NMR spectrum. And if the motion is faster at higher frequency, then we will see sharp lines, and if it is slower, we'll see broader lines. And I'm talking about, when I say fast or slow, I'm talking about frequencies of 10 to the 10 to 10 to the 8 per second. This is about 6 orders of magnitude faster than the resolution, than the shutter speed of a photographic apparatus. So there's no way you could get sharp pictures with photographic methods. We had to think about something different. And this something turned out to be the distance between two atoms. Distances are scalar quantities and are therefore independent of rotational and translational motion. And I illustrate this here with this slide. Each of these circles represents an atom. At first it was always hydrogen atoms, they could be different ones now. And you see that we have short distances between pairs of atoms. And this distance is always the same, independent of whether we look at the combination of two circles in the lower right or in the upper left, or whether the link between the two is horizontal or vertical. That's the properties of a scalar. If we are able to measure such short distances between atoms, then we could, in principle, solve the problem of a structure determination. And we have this method. One of the first two-dimensional NMR experiments that we developed was NOSY. See, we had COSY, NOSY, SEXY, and FOXY. These were the 4 two-dimensional experiments that we had developed in 1982, and these were enough to determine the first protein structure. And NOSY is the one that gives us information on short distances between hydrogen atoms. This is a small part of an OSI spectrum from 1983. So that's very old. Today it would look much better, but this is already quite beautiful. Now each peak in this contour plot of a two-dimensional OSI spectrum tells us that there are two atoms at the close distance in the protein structure. Now we can measure a few hundred. Originally we could measure a few hundred such distances. Today we can measure maybe 1,000 or 2,000. But whenever we apply these distance constraints, we also have repulsion between the atoms. And so this means that in all, by analyzing the OSI spectra, we get a few thousand distance constraints. And using distance geometry, molecular dynamics, minimizers, so on, we get the molecule in 3 dimensions. Okay? From here, OSI spectrum to here, we get 3-dimensional structures at atomic resolution. And that's what I got the Nobel Prize for, to have solved this problem of how to deal with structure determination of proteins under the regime of Brownian motion. Now, I talk too long always. I have used up my time. Should I go on for 15 minutes? Yeah? All right. So let me talk about what we are doing today with this. You see, a different presentation of 3-dimensional structures from the ones that I have shown here, where the atoms have no dimension, is here in a space-filling model. And in this presentation, you get that's a picture you got from X-ray crystallography. And then in 1974, we discovered that there was a lot of motion in these tightly packed proteins. And the observation was that the rings of phenylalanine and tyrosine undergo 180-degree flipping motions inside the folded protein. That's like this, you see. These, on the left, you have a picture of these rings of phenylalanine and tyrosine. And you have the positions 1 to 6, where 3 and 5 and 2 and 6 are symmetry related. Therefore, in an isotropic medium, these cannot be distinguished. If the rings are embedded inside a protein, then 3 and 5 and 2 and 6 are no longer equivalent. And when the ring flips over, we can measure the frequency of this flipping motion. And whenever the ring flips over, a few hundred atoms have to move out of the way. And this has now been shown to be true in all proteins, membrane proteins, soluble proteins, and we still have not fully understood the functional role of this motion inside proteins. We first measured these ring flipping motions in a small protein with the name of basic pancreatic trypsin inhibitor. The important thing to show is that one of the rings flipped 300 times per second at room temperature, another one faster than 10 to the 4 times, one 50 times per second. And this puzzled a lot of scientists at the time. And I just listed here some publications from 75, 78, and 80, and those names who are listed in red are scientists who obtained the Nobel Prize in the meantime. So we have 1, 2, 3, 4, 5, 6, 7 Nobel laureates who worked immediately on trying to understand these ring-flipping motions that we described in BPTI. And most important perhaps today, when we have to assess the development of AI and similar techniques, is the fact that when you go to the bottom of this list, you find another name of a Nobel laureate jumper. He is not yet red, I haven't remade the slide, but the fact is that it took computational colleagues working with computational methods 36 years to develop a computer, hardware and software that was capable of simulating the ring flips in BPTI that we had observed in 1974. 36 years between the experimental observation and the simulation with molecular dynamics techniques. And it will also in the future be so that we first have to do experiments, find new things, and then we can use the computer methods to try to explain, to rationalize, and to go on from there. What are we doing with this today? We are studying GPCRs, G-protein coupled receptors. And I'm doing this work with a team at Shanghai. You see here the picture of the students who currently work with me. We are about 15 of us. We all work on GPCRs. Now, what are GPCRs? GPCRs are membrane proteins that transfer signals across cell membranes. They are extremely important. We have 826 different GPCRs in our bodies. About 40% of all FDA-approved drugs target GPCRs. And only about 40 GPCRs have so far been targeted by drugs. So we have a long ways to go to study GPCRs and to try to expand druggability to a larger representation of this huge class of membrane proteins. That's what it's all about. At the top, you have the outside of the cell, at the bottom, the inside. At the top, what it says, orthosteric ligands and allosteric ligands. That's where drug molecules would bind. And there is a signal going across the membrane to partner proteins, G proteins, arrestins, possibly kinases. And you cannot understand, in 2007, the first crystal structure of a human GPCR has been published. Today, we know crystal and cryo-EM structures of about 300 different complexes of GPCRs with ligands and partner proteins. But all these structures taken at liquid nitrogen temperature cannot explain how the signal goes across the membrane. We need to measure this at body temperature or close to body temperature and in a solution environment, and that's what we are trying to do with NMR. And I show you one particular experiment to indicate to you in which direction this goes. I'm talking about a particular GPCR, the neurokinin 1 receptor, which has a lot to do with brain function, so on. What you see in this slide is the crystal structure of NK1R, which is one of the few crystal structures that I actually co-authored. I didn't like to do it, but we had to do the structure by crystallography because it's much more efficient than by NMR. In the middle, you have a prepitant. You have a chemical structure. This is a drug that has been approved already more than 10 years ago to fight nausea during chemotherapy for cancer patients. And when you look at the structure, then at the bottom, you see a phenyl ring with two trifluoromethyl substitutions in chemically equivalent positions. Okay? Now this drug goes from the top, from the outside of the cell membrane into the orthosteric binding site. When we dissolve that drug in a solvent, then we get a single line because of the chemical symmetry of that substituted phenyl ring. If we place it into the protein, then we have different environments of the two trifluoromethyl groups, and we can now measure the exchange between the two, if there is exchange. And indeed there is. You see the red arrow on the right, that ring with the two trifluoromethyl group flips over by 180 degrees at a certain frequency. And this we can determine with two-dimensional exchange spectroscopy. And what we find is that the opening of the orthosteric site is much larger than one would have guessed from comparing structures with different ligands bound done at low temperature by crystallography or by cryo-EM. The opening is at least twice as big as had been suspected before. Now this has important implications for drug design, because we now know that the orthosteric site can accommodate much larger ligands than those that one had guessed before, and that the secondary recognition process occurs only after the initial binding into the orthosteric site. And this is greatly affecting the ways we think about choosing candidates for drug design that should target particular GPCRs. We have performed similar studies at the other end, and we again have, this has just recently been published, we find that intramolecular mobility plays a key role in enabling the transfer of signals from the outside of the cell membrane to either G proteins or beta-arrestins. So that's a kind of applications that we make today of this technique. It all started with dynamics, Brownian motion, and it goes on with dynamics, intramolecular motions. I finish with something that seems at first very different. NMR can also be used to study human bodies, as some of you have probably experienced yourself, and not only molecules. We refer to magnetic resonance imaging. Why do I bring this up here? Because the principles that I have described to you at about half an hour ago apply here. When you do MRI of a human body, you only look at the water. You only see the water because only the water moves rapidly in our body. Bones and muscles, so on, don't move, they are not seen by an MR. And that is why we can do MRI in the hospitals. And I had the first laboratory in the Children's Hospital in Zurich in 1985. That's also quite some time ago. I stopped doing MRI when it became common. At that time, it was very exciting as a complementation of what we did in studying molecules. And again, as early in my career in the 1960s, I was again looking at the waterline in newborn babies and studying their brains and the development of brains and damage to the brains. Now, how is it done? You only look at water, so you have to distinguish water in different parts of the body by changing the magnetic field. You apply a magnetic field gradient, that is this skewed line, so that you have a different field on the left and the right of the head, and by very similar techniques to those that we introduced for multidimensional NMR, you can then develop pictures of parts of human bodies in such a machine, which is here presented by one of the colleagues who obtained a Nobel Prize in 2003, Peter Mansfield, for MRI, together with Paul Lauterbur. And most people then show heads, brains. I don't need my brain very much, but as was mentioned, because I was playing soccer and skiing and swimming, that was my main profession. That picture is not very old. It's a shame. Now I'm using a stick, probably because I played football too much. So that is only 12 years ago, the FIFA exhibition game. And I needed to see my knees. And you see, these are also new pictures, relatively new from 2016. And that's a kind of resolution you get when you look at the really important parts of your body. And fortunately, my knees did not need any surgery yet. It's only the hips that have given up. And I hope this will stay like this. So, you see, MRI can be understood with the principles that I've explained to you, the influence of Brownian motion, Einstein's analysis of Brownian motion, work that goes back 2 centuries and 120 years. You have to read the old literature, and that helps you to be innovative all of a sudden and develop methods that can be useful in everyday's life. Now, I want to finish with structural biology and mention just one more item. This is a picture of the prion protein from cattle, from cows. And this is a protein that caused mad cow disease. During the crisis of mad cow disease in around 1995 to 2005. And what we discovered in the structure of the prion protein was that only 1/2 of the structure is folded. That's a green, blue, and yellow part. And an equally large part is not structured. And it's flexibly disordered. Here we have a superposition of 20 snapshots taken at time intervals of 20 picoseconds, 20 times 10 to the minus 12 seconds, and that's what you see. And today, a large part of structural biology is devoted to study intrinsically disordered proteins. That is, proteins and nucleic acids that do not show a defined three-dimensional structure when studied with the available experimental methods. It's guessed that 30 to 40% of all proteins may fall into this category. This was the first one that had been characterized as an intrinsically disordered protein, and it is part of the secret behind diseases like prion diseases like Creutzfeldt-Jakob disease in humans, scrapie in sheep, mad cow disease in cattle, and so on. And this is currently one of the very big areas of application of NMR structural studies of proteins in solution. Thank you.
For his wonderful speech. I think the floor is now open. I think you have time for questions. Okay. Oh, just a bit here.
You just say that the atom would rotation as the Brown observed, and I was wondering that if the structure would have a mirror structure, and if the level rotation would have the same function as the textual rotation with G protein that transmit the signal transduction. And the mirror structure, level and the textual. The level and textual structure would have the same function, or it's not a different molecule to identify it.
I don't know whether I understand your question properly. I mean, GPCRs are fixed in the micelle. They are fixed in the cell membrane. And in order to perform studies by any of the methods, crystallography or cryo-EM or NMR, we at the moment have to get them out of the membrane and place them in membrane mimics that allow us to prepare a concentrated solution that shows sufficient rotational motions so that we can record NMR spectra. Okay? Or crystallographers that they can grow crystals. Or cryo-EM methods to place sufficient material on their grids. And we cannot, at the moment, study the membrane proteins in their natural environment. That's a question of sensitivity, among others, and in the case of NMR, that we wouldn't see it because we would need to use solid-state NMR, but then you wouldn't get the same kind of information on dynamics that we see in solution. But did I understand your question correctly? I mean, this has nothing directly to do, I mean, the rotational motions I was talking about have nothing to do directly with signal transfer across the membrane.
Okay, thank you.
Good afternoon, Dr. Wüthrich. This is Hong speaking. My question is there any application of electrospray ionization for the development of new pharmaceuticals?
I didn't understand the
question.
Question.
Dr. Chung Fan's breakthrough is softer ionization and the multiple charging. In terms of the development of the new pharmaceuticals, is there any application of ESI, electrospray ionization?
Well, ESI is widely used in proteomics. It's indispensable as a method. I mean, mass spectrometry has revolutionized the science of protein studies in not structure determination, but protein upregulation, downregulation, simply what is usually summarized as proteomics. It's widely used. It is much more widely used than NMR, because it's also much easier to do than NMR.
Hi, I'm Chen. I'm a chemist working on proteomics. And I would say that the high-resolution protein structure is very important to inspire a lot of pharmaceutical development, like target therapy. But I'm working on membrane proteins. And in terms of the protein structure, it's still so difficult to resolve the three-dimensional high-resolution structure. So I'm wondering what's your view or suggestion to further advance the protein structure on the membrane proteins? Thank you.
Well, you see, today there is a great hope that drug development would be greatly helped, made more efficient with the use of structure prediction by these artificial intelligence methods. So far, I don't know about a single case where a drug was developed on this basis. What is more likely is that you get very convincing indications from modeling, and you would then repeat the study experimentally. And this is the way it is going. You see, these model predictions greatly help the experimentalists. You see, if you have a nearly precise model to start with, the structure determination of a new protein may be done in 3 days rather than 3 months. That's what I'm talking about. And that, of course, has a big impact on drug development. But what is a weakness that is left is to predict binding sites for drugs that you probably encounter in your work. And you see, this is a bit difficult. If I say that it cannot be done, then I'm making a fool of myself, because it will probably happen that one of these predictions leads to a drug in the next few years. But I think that's how you should see it. You should see that these structure predictions with alpha 2 and alpha 3 would greatly speed up the process of finding candidates for drug development.
I also have additional comment on the GPCR. It's so wonderful to see that you are working on GPCR. At this moment, we still have 7% of missing protein from human proteome. And 50% of them are the very small GPCR. So I think it's very important to identify all these unknown missing GPCR. And that could be very useful to find more therapeutic development. Thank you.
Thank you.
See you.
Hi. I'm Dama Yu from IMS. I work on solution NMR. I actually postdoc Gerhard Wagner, so I'm scientifically your academic grandson. My question is not scientific, it's more like, I believe you have been working closely with many talents, like managing a big groups. What is your secrets of keeping everyone motivated?
Of keeping
Everyone motivated.
Okay.
motivated. See, if you ask me, I was teaching skiing, and I was teaching swimming and jump board diving. And there I could give you a straight answer, and that is, show them how it's done. Okay? I would show how to ski, and they should do the same. In science, it's probably also by example. I mean, they must feel that I'm really interested in what we are doing, and that I see goals ahead, and that I am sure that it's worthwhile to do it. I don't know how direct this goes through. In sports, it's a very clear thing. I mean, if I can't do it and show it to those who have paid me to teach them skiing, then it's lost. Okay? I cannot explain to someone how you do a turn to the left if I cannot make a turn to the left on ski. You see? And I consider it a little bit the same in science.
Hi, my name is Wên-Chang Liu. I think in 2022, right before the Nobel Prize announced, you spent 1 week in Taiwan.
Yes.
To deliver several lectures. I'm honored to host your lecture in National Tsinghua University.
Yes.
Nice to see you again. And my question is, I'm also working on the AMR for protein structure. And for the structural biologists, we spend so many time to work on the X-ray or AMR to get a structure. But this day, the student just by a click, they get a structure by AI like AlphaFold. And what's
They don't get the structure, they get a model.
Okay, I agree. They get a model, but the student or the pharmaceutical use that model to do a lot of things used to be only structural biologists can do. So what's your opinion to attract people to study the AMR or X-ray again?
This is a problem with the students. This is certainly a motivation problem. But you see, when you listen to the guys who developed Alpha 2 and Alpha 3, they are very careful to emphasize that their method only works because they have the 200,000 experimental structures to train their algorithms. And if you have proteins that are outside of the conformation space covered by these 200,000, or today it's probably 240,000 experimental structures, then the prediction methods are in danger of failing, or at least being inaccurate, but more likely to simply go astray. Okay? Today, a new class of very small peptides or proteins, whatever you want, with 5 to 30 amino acids have been discovered to have extremely important roles in physiological processes. And these small molecules cannot be treated at the moment with anything but NMR. Intrinsically disordered proteins cannot be treated with anything else but NMR. And the kind of information that we get on GPCRs and on the interaction of GPCRs with their ligands cannot really be obtained with other methods. And that's just a fact. We are not at the end of experimental studies. It is most likely, probably, that a large part of the information that has so far been obtained with X-ray crystallography will be obtained with structure predictions. That is, even this is debatable. But what cryo-EM is contributing and what NMR is contributing in terms of dynamics, I think we are years away from modeling to predict these results.
Okay, I see young face.
Vielen Dank für die wunderschöne Vorlesung.
You have to speak up.
In English. Yeah, I was speaking.
Do you have a microphone?
Here, yeah.
Yeah.
Yeah. Also, vielen Dank für die wunderschöne Vorlesung. And my
She
question.
speaks German, in case you shouldn't notice.
And my question is, you must have a lot of opportunity to witness how important techniques, methods develop, like how people before that technologies and after that technologies work on things. So what do you think is the differences, how people see things and approaches problems every time new technologies evolve?
Well, methods development has always been an important step in the development of all sciences. I mean, in chemistry, when I was a student, which is long ago, I also had to do chemistry lab. There was no NMR, and there was no infrared spectroscopy, no Raman spectroscopy. And I think all structure determinations had to be done by derivation of, you probably don't even know what it is, derivation of organic compounds to identify their structure. And when you look through the Nobel Prizes in chemistry, about 1/3 has been given for methods development. That tells you all about how important methods development is.
Like how people changes how they see things and approach problems. Like today, like we have AI, of course, like the students would rely a lot on AI, then that they might take a very different approach in seeing the problems or trying to get to what they try to assemble. So I don't know, like, is it like today?
No, imagine what would biology be today without DNA sequencing or without GPCR, structure determination in my case. I mean, these are all methods developments. You see, I mean, once PCR was introduced, the work in the lab changed. Just within 2 years, the lab was different. I mean, there are many methods developments that have changed the daily practice in the laboratories forever and completely. And this happens faster and faster. That's what I meant with the text that I showed early in my talk. You have to adapt, you have to go with it, and if you don't, you fall behind. And this will continue. There will be further developments of methods that will again and again change the ways we are doing things.
Thank you.
That's your chance, those of you who are a little younger than I am.
Okay.
Thank you very much.
Over there, please.
Hello, thank you for really great talk. So I have questions. For MNR analysis, proteins are usually introduced into bacteria, then labeling with the isotope and purified. But under these conditions, so for example, I look into the human proteins. So is the structure still presentative? Is native stage? And how can we, how much can we believe in the results?
Well, the question is, to what extent are the properties of recombinant proteins the same as of the natural proteins? Yeah. I don't think I need to discuss this here. If the recombinant proteins contain all the components that the natural protein contains, there is no reason for a chemist to believe that they behave differently. The problem may be that if you express the proteins in E. coli, they may not have all the post-translational modifications that are needed for their proper functioning. But this we are dealing with all the time. Does that satisfy your question? Is that an answer to your question, or did I misunderstand you?
In that case, so how can we dealing with this issue?
Well, then you have to try to express the proteins in a different system that ensures the post-translational modifications. That we express, I mean, GPCRs cannot be in practice expressed in E. coli. So we have found systems to express them in yeast. And then we have solved the problems you are alluding to. And another one is SF9, a viral system. It's much more difficult, much more expensive, but you cannot do everything. If you get stuck with proteins expressed in E. coli, you have to go to more expensive systems.
Yeah, thank you.
Thank you. I think we have many young scientists, but I think you start with education. So I have a question. I look at your YouTube, and then you mentioned about when you start your work, you spend 4 years trying to convince people, say, yeah, I'm right. I'm just wondering, during that period of time, how do you feel, and how do you try to overcome these people who doesn't believe in you?
You want the truth?
Well, I think the young people need the truth because they may one day see people don't believe in them.
Okay, the situation was the following. We solved two structures in 1984 and 85. One of the two structures was metallothionein. And that was entirely new. And colleagues using crystallography also solved the structure. And they solved it wrong. It was completely wrong. I mean, that protein includes 28 metal to cysteine bonds, and 21 of those were wrong in the crystal structure. And then science decided to publish the wrong crystal structure, and we couldn't publish our structure because a different structure had been published in Science. And it took 7 years before the guys repeated their structure determination and found that their new X-ray structure was identical to the one that was in 1992, was identical to the one that we had found in 1985. How do you survive this? Bah! It probably cost me the Nobel Prize in 1991. That was the reason why I didn't share the prize with Ernst in 1991. You see, that's what you are asking, right? That's what happened. What did I do initially? I left the university and went skiing. I was skiing from 1984 to 1986. 2 full seasons. It was beautiful. I was in great shape. In the summer I trained for good condition, and in the winter I skied every day. That's what I did. And I wrote the book, which is still in sale, which has been reprinted some 40 times in the meantime. And sure. But that's what I did. Initially I went skiing, and then we waited for these guys to repeat the structure determination and admit that they were wrong.
Okay. Thank you. No more? Okay. There's one question.
Hello, thank you for your talk. I you've mentioned many times that you studied in, you taught gymnastics, swimming, sports, and as well as also these lectures and such. Can I ask how you stay very much prominent in all of these fields that you are interested in? Not just one, but in all of them, like simultaneously, and also like your sabbatical, how you wrote your book, but it was also skiing. And I think that's quite very impressive. Yeah.
Well, look, I also have, I wasn't just skiing. I have a university degree in sports. I have a master's degree in sports education. Okay, I did this in a serious way. I was teaching sports in high school. I was teaching ski in ski resorts. I was teaching swimming, private lessons. That's how I made my money early on. When we went to the United States first, my wife and I got stipends to study American sports because that was of interest to the Swiss schooling system. So I learned to play basketball and volleyball in the United States. But on the side, I did quantum mechanics and on a level that gave me a job at Bell Labs, if you know what that means. Bell Labs was the best laboratory that ever existed, any time in history, anywhere in the world. And this all went together. You see, doing sports, studying sports made me study medicine, pre-medicine. I had to do pre-medical studies. That was very important later on. Just as it was important to have a degree in mathematics and physics. But my first really impactful papers were on oxygen binding by hemoglobin, because I was in sports. And oxygen binding is very important. Oxygen uptake is extremely important in competitive sports. And then, I mean, until 10 years ago, I was a member of the International Anti-Doping Agency because of blood doping. I was a specialist in blood doping. That has a lot to do with NMR. You can check this yourself. I have papers on hemoglobin, and I showed you cytochrome C, but this all came from having done sports. I wouldn't have come on my idea to study my blood. I used my own blood. I didn't study some hemoglobin. I studied my own because I wanted to know whether I could learn something to perform better. I was still running at that time. I was less than 30 years old, so I could have used the information. So it went together. It was, you see, I mean, when I needed a new NMR machine in the mid-1970s, I would go to the president of the ETH and tell him that if he didn't have the cash to buy it, I would leave the university and coach the soccer team, where I would have 3 times higher salary than a professor. Could have done that. It was a game. It all went together.
Okay, I think the time is up. So thank Professor Wüthrich for sharing with us all this wonderful
Well, they make me say stories here that I should probably not.
And let's give the warmest and the biggest applause for Professor Wüthrich one more time. Thank you.
Okay, let's.
Ladies and gentlemen, we thank you for your participation today. Our next Nobel Laureate lecture will be on 23rd April. We look forward to seeing you soon.